Hi everybody and welcome to today's lecture on climate change. In this lecture we're not just going to talk about what climate change is and how it works and the mechanisms behind it, but we'll also talk about the lines of evidence that provide our insight into those mechanisms, and we shall also talk about why climate change is not universally accepted. So how evidence can be distorted and some of the other issues. Okay, so it's not just a pure science lecture, it also incorporates parts of social ideas and politics and things like that. Okay, so I'm just going to start sharing my screen. Let's find the PowerPoint, there we are. Okay, so by the end of this class, you guys should be able to explain what global warming is and the difference between climate and weather, compare the different sources of evidence that we have and how they relate to climate change, understand why climate change is not universally accepted. So let's start off. So first up, what is climate change? So climate change is a phrase we're all probably very familiar with at this point, but what actually is it? How does it relate to a whole bunch of other components of weather and climate and anthropogenic activities? And what do we mean really when we say climate change? Well, the first thing we have to understand is that climate does not equal weather. Climate and weather are related, but they are not interchangeable. We'll talk about the difference specifically in a minute. And this sort of mistaking and intertwining of climate and weather is how a lot of people sort of argue against climate change. So, for example, NOAA find 2014 to be the warmest year in modern record. So, in a debate on climate change in the House of Congress, the GOP science denier Senator Inhofe brought a snowball onto the Senate floor to say, "How can there be climate change? There's snow outside." And this argument, or versions of this argument, you'll hear time and time again. Whenever it's a really sudden cold snap and you get a massive snowstorm, people will sometimes say, well, that's climate change done then. Or they do the exact same thing as this. How can the climate be changing? It was really cold the other day. It's really cold out today. That's the end of climate change. The reason for this is people don't understand the difference between climate and weather. So one of the examples of this, it's been really hot. The 2010s were the hottest decade ever, yet we were still getting these weird climate anomalies. So in 2017, one of the warmest years on record, the UK was hit with a massive snowstorm, the biggest snowstorm they'd seen in decades. This is a satellite image of the UK. The entire country is white. We never get this. London Bridge was covered in snow. As an indication of how bad we are in the snow, the amount of car crashes went through the roof because we just are so unaccustomed to driving in the snow that we had no idea what we're doing. So even though it was a really, really hot year, we had this short, very cold snap. And so people are then saying, well, how can climate change be occurring? We're having massive snowstorms. But let's have a look at what's actually predicted. So overall, by about the end of this decade, or the end of this century rather, we're predicting up to about a 3-degree increase in temperature at the equator and about a 5 to 8 degree increase in temperature at the poles. The poles are going to be more badly affected than the equator is. The average global prediction is about 1.8 to 4 degree increase. What have we observed already? Well, we've seen in temperature records a 1 degree increase in world temperatures since 1900. The year 2000 to 2010 was the warmest decade of the previous 1,000 years. 2003 was the warmest year in over a century, according to the IPCC. 2004 was even hotter. 2005 was hotter still. 2010 was the hottest year ever on record. 2014 broke the record set by 2010. 2015 broke that record, 2016 broke that record, and 2017, 2018, 2019 and 2020 are all in the top 5 hottest years ever recorded. Now I can present this sort of evidence of observed changes in temperature as a list like this, but someone has done it much better than me. So I'm going to show you a graphic. Let's just stop sharing here. Hello. And we're now going to go and start sharing a different screen. Here it is. So you should now be watching a YouTube video. All the links for these are inside the slides as well, if you want to actually go ahead and watch them on your own. So this is a graphic. I'm going to just expand it. This is a graphic showing temperature change through time all around the world. So around here we have all of the different countries of the world. They're grouped by continents. We've got Oceania, America, Europe, Asia and Africa. And what we're going to do is count up years from 1901. And this, the longer the bar is, the hotter it is. Zero, this zero here, is the average. This is showing no temperature change at all. So this is the average over this 100-year period. These blue bars, whenever it's blue, it means that that place, that year, the temperature was below average. Orange or red and increasing levels of heat. Above that means in that year, that country was above average. So just make sure we're totally orientated with this. Let's look at the year 1901. This section of Africa, so Gabon, Gambia, Ghana, Guinea and Guinea-Bissau, were all a bit hotter than we'd expect. They're about a degree hotter than we would expect. As was Senegal. Conversely, Australia and Fiji were a bit colder than we would expect overall. So what we can see is every year we've got some countries that are hotter and colder. What we're now going to do is run this through time and watch what happens. So remember, this zero is the average over the course of this timescale. So everything's pulsing in and out, above average, below average. It keeps pulsing, and then in the 80s it really starts to increase. All of a sudden we're seeing a lot less blue and a lot more red. And it gives red and red, and gets more and more extreme. Until the extent we get to 2016, which of course remember was the hottest year on record. We're now observing multiple countries that have recorded annual temperatures 2 degrees hotter than we would expect on average. Not a single country anywhere on this graph is less than 0.5 degrees hotter than we would expect, and there's nowhere obviously that's gone blue that's below. So this figure through time shows you a bit about how the climate is changing through time all over the world. Okay, righty, we'll just stop sharing this one and we'll go back to let's start sharing. Sound down. Let's go back to our PowerPoint. So that's where we were. But we've got this change, we've got this evidence showing increased temperatures, and yet, just to reiterate, we've got the UK showing one of a huge gigantic snowstorm, the biggest snowstorm it's seen in generations. So what's going on? Well, it's the difference between climate and weather. So weather is the current state of the atmosphere around us at any time. So you would say, like, what is the weather like today? Well, it's sunny, it's hot, it's cold, it's raining, it's hailstorming, it's a hurricane. Like, that is the weather at any given time. Climate is the long-term description of weather, including average conditions and the full range of variation. So, for example, in Logan, Utah, what is our climate? Well, it's reasonably arid. It's quite dry, we get cold winters and hot summers. You wouldn't say, what is the climate like today? Because that wouldn't make any sense. The climate is a long-term description of weather. Weather is what's happening today. You would say, what is the weather like today? But what is the climate like today doesn't make any sense. So climate is a long-term description. Weather is what is happening at any given time. And climate change refers to a directional change in this climate over a period of several decades. We're not talking about a one-off day where it's one thing is doing something different than usual. Okay? So then the question is, well, what is driving these changes in global climate? And critically, is there an evidence for a crucial link between CO2 and temperature? Well, yes. So let's have a look at a couple of these. First of all, we're going to look at the long-term evidence for a link between CO2 and temperature. And what do we mean by long-term? We mean hundreds of thousands of years. Unfortunately, we have one of the most incredible data sets on the planet that can actually give us this information. This is because the concentration of CO2 in the atmosphere at any one time can be measured in tiny bubbles that are preserved in polar ice. So when the ice forms on the polar ice caps, it traps tiny amounts of air in that ice, and because the ice caps stay cold and frozen for a very long time, we have a little miniature time machine of little tiny samples of air going back hundreds of thousands of years that contain the concentration of CO2 in them that was present in the atmosphere when that ice formed. And these concentrations in the ice are correlated with glacial and interglacial cycles, and what we see is the lowest concentrations correlate with glacial periods. And so this is what these sort of things look like. This is the most famous of these is the Vostok ice core setup in Antarctica. This goes down thousands of meters deep into this ice, and you take these ice samples, and what you do is you take a little drill out and you then measure the CO2 preserved in this ice. You can work out how long the ice takes to form, and that tells you how long ago it was. But critically, the structure of the ice and how that ice is actually, the crystalline structure of the ice, is determined by the temperature at the time that ice was formed. So we've got this record where we can simultaneously measure the amount of CO2 and the temperature back through time, going back a very long way. And what does it look like? Well, here's what it looks like. We've got on the x-axis we have thousands of years before present, so this is us here now, and we've got several y-axes going on at the same time. Okay, so on these two we've got the concentration of CO2, which is our main greenhouse gas. We've also got the concentration of methane, CH4. On this we have the temperature relative to the present climate. So our red line is the temperature over Antarctica. The black line is the atmospheric CO2 concentration. The green line is the atmospheric methane concentration. And what we can see is, going back thousands of years, hundreds of thousands of years, we've got this very tight coupling between CO2 and temperature. And these big pulses are taking hundreds of thousands of years, remember. So although we have got, this looks like a massive jump, but that's a change over tens of thousands of years. But through this sort of long-term time frame, we have all of this really tight coupling between CO2 and temperature. So that gives us a long-term indication that we have got this tight coupling between CO2 and temperature. We also have short-term evidence for a link between CO2 and temperature, and one of the best ways from this is from a place called Mauna Loa in Hawaii. So there's an observatory in Mauna Loa in Hawaii that is taking CO2 levels, and it's also measuring temperature through time. Can anyone think about why specifically it's been done at Mauna Loa in Hawaii? Well, Hawaii is one of the most remote pieces of land on the planet. It sits literally in the middle of the Pacific. It's therefore a great place to measure CO2 because it's about as far away from a big major industrial city as it's possible to get on the planet. So what we've got is this place where we can measure sort of the global baseline of CO2 without it being interfered with by nearby cities, and we're taking the temperature. And what we see is, so here's our time period again, now only going back 8,000 years before present, so here's us. So here's the birth of Christ, and that's 8,000 years going back. We've got our ice cores here, then we've got a more modern ice core, and then we start the Mauna Loa temperature weather station, and we can see these things line up, and we can measure the CO2 levels and temperature over the last 10,000 years. What's interesting is if we compare this graph with human population over the same time scale, it looks very similar. We dinked along, CO2 levels aren't super high, and suddenly they shoot up. People do the same thing. There's a bit of the bubonic plague where we all went down, and then we shoot up as well. So we've got this big correlation between CO2 levels and number of people. And the main source of anthropogenic emissions and atmospheric CO2 concentrations are burning of fossil fuels. Burning of fossil fuels does two things. First of all, it puts particles into the air. Here in Utah, you might hear a lot about the PM 2.5, which is one of the really nasty air pollutants that we get. But also, burning fossil fuels throws lots of carbon dioxide into the air, much more so than we do by breathing. The particulates are a bit of a problem. This is an image of China, in a very industrialized part of China. This is the industrial powerhouse of the world. This is PM 2.5, so it's that nasty smog that clogs up your lungs. This was an image taken by a friend of mine when they were on a visit to China, trying to look at some of these beautiful Chinese temples. Unfortunately, this is what most of them looked like because they were so buried in smog. But the other thing I want to draw your attention to in this is, yep, we get good old McDonald's absolutely everywhere. This is not a problem that's unbeknownst to us in Utah, though. These are images of Logan and Salt Lake City. And these are images that are taken during the temperature inversion when we end up with really serious smog problems and particulates in the air in Logan and in Salt Lake City. So let's have a think about this CO2. Think about, we've talked earlier on in this class about measuring ecosystem functions, so rates of things getting moved around. And the CO2 is all about things getting moved around. The major pools of carbon on the planet are in the atmosphere, the oceans, the land surface, such as soils and vegetation, and sediments, such as rock, so things like coal, oil, limestone, chalk, etc. All of these are pools of carbon. They're where carbon sits. Now, 99% of global carbon is in sediments and rock. Now, these sediments and rock are the most stable pool of carbon on the planet. It takes up and releases carbon on geological timescales. So things like this is the White Cliffs of Dover in the UK. It's made out of pure limestone, which is why it gives it its white colour. And that is a huge lump of carbon. Calcium carbonate is what makes that limestone. In addition, all this coal and the gigantic coal mines that are present here in Utah, they are huge pools of carbon, and getting that carbon out of the atmosphere into those pools, so turning atmospheric carbon into this limestone or coal, takes thousands if not millions of years. It's on geological timescales. And so if we have a look at, just a quick look at the global carbon cycle, something interesting comes up. So each of these numbers represents gigatons of carbon. And the arrows represent fluxes, so rates of carbon moving between pools. And these boxes represent pools of carbon, sort of static carbon. So for example, the surface ocean waters contain about 920 gigatons of carbon. And the amount fluxing between the atmosphere and the ocean waters, well, 91 gigatons is fluxed from the surface waters into the atmosphere. 92 comes from the atmosphere back into the ocean waters. And we look at some of these numbers. So surface ocean waters contain about 920 units. The marine biota, that is the animals and plants in the oceans, contain only about 3 units. It's much smaller. The deep ocean water, so not the water on the surface, that contains about 38,000 units. So this is enormous compared to this. The atmosphere contains about 700 units. Soils, all of the terrestrial soils contain about 1,500 units. The vegetation that's on those soils contains about 650 units. But look at the biggest pool. 6 million units, 60 million units, are present in rocks. So this is by far the biggest pool of carbon. Now let's have a look at some of these fluxes. Well, here is us burning fossil fuels. It produces about 7 units, fluxed from the land into the atmosphere. Land use change, so deforestation, cutting down trees, that contributes about 1.7 units. So these numbers actually look quite small. Look at the size of these numbers in comparison to things like the atmospheric ocean flux. This is over 10 times bigger than everything we're doing. Also, when we look at things like gross primary production, so this is the carbon that's taken up out of the atmosphere by plants photosynthesizing, we can see that's 123 units, and respiration by all the plant animals is 120 units. So look at this. These numbers are about 20 times the size that we're doing by fossil fuels. So these are natural processes, and they're moving hundreds of units of carbon in and out of the atmosphere. Our anthropogenic activities are moving a much, much smaller amount. So you'll often hear people talking about, well, fossil fuels only contribute, 0.5% of all of the carbon getting fluxed into the atmosphere. Look how much is getting put out by respiration of animal and plant life. This is entirely true. We're contributing a tiny amount to the atmosphere in comparison to natural respiration or atmospheric ocean flux. So why is this then such a problem? If it's a tiny amount, why is it such an issue? The reason it's an issue is because look how tightly coupled these numbers are. So the amount coming out of the atmosphere is 123, the amount going up is 120. The amount here going out is 91, the amount coming in is 92. So these numbers are really tightly correlated. And if you've got a really tightly balanced system and you put just a tiny amount extra in, it becomes quite problematic. So say, for example, you decide every day you're supposed to drink more water. This is what we're being told all the time. You've got to drink water. We must drink at least 2 litres of water a day. Your body is set up in a way that it can process 2 litres of water quite easily. Each litre of water weighs a kilogram. I, at the minute, weigh 80 kilograms. So let's say I'm drinking 2 litres of water a day, my body can process it just fine. Let's say, for example, I decide to increase that a tiny amount. So I increase it by half a litre. So I now drink 2.5 litres of water a day, but my body is unable to process that extra half litre. So even though I weigh 80 kilograms, because I'm adding an extra half kilogram every single day, that means in just a year, my body weight would more than triple, because I'm just now a huge ball of water. Because even though that each amount I'm taking in is a very small number in compared to how big I actually am, it's not getting processed. And the same is true with fossil fuel emissions. Although the amount going out is actually quite small in comparison to natural processes, it's not being processed, and so it's continuously being added into the atmosphere. And it's building up, and that's why it's a problem. Even though it's tiny, it's in an excess. Okay? Because prior to the Industrial Revolution, the fluxes of carbon between sediments in the atmosphere were roughly equal, which meant we had no net change in atmospheric CO2. Human activity only produces about 5% of natural emissions. Most of this is due to burning of fossil fuels, so 80% of the carbon we produce due to fossil fuels, about 20% is due to deforestation. So although human activity is a tiny amount, the fluxes are no longer equal, and that's why it's a problem. So, let's have a quick fake clicker question. So, where did the Earth's carbon originally come from? A, humans have produced it with their activities. B, it was produced prehistorically by the activities of animals and plants. C, the carbon was produced when the Earth was formed. Or D, it was produced through nuclear fusion within stars. It is older than the Earth itself. Just give you 10 seconds on this. So, the answer to this one is D. The carbon on Earth was produced through the nuclear fusion within stars. That carbon is older than the Earth itself. There's only one way, predominantly, that new atoms, sort of atoms of carbon, get produced in the universe, and that is through nuclear fusion within stars. Human activities, we can now do nuclear fusion as well. It's what powers our nuclear power stations. But that is a tiny amount, like a microscopic amount compared to what's going on in stars. So our carbon was produced inside stars like our sun through the carbon fusion cycle. Protons and electrons getting added to molecules, and so we're getting molecules to atoms, and so we're changing the atomic structure of these different elements. And then what happens is when this star goes supernova and explodes, the carbon and all the other elements it produces are fired out across the universe, and some of them eventually ended up in our planet when it formed. So then the question becomes, well, if all of this carbon has been here since before the dawn of the Earth, what's the issue with it now? All the carbon that's ever existed on our planet is still there. The planet itself has never produced any brand new carbon. We've never got rid of any carbon either. So all the carbon that's ever existed on our planet is still there, and none of it has gone anywhere. So what's the issue with it if it's always been there? Well, the issue is it's not producing new carbon. The issue is disrupting the fluxes of carbon. It's moving carbon between the pools on the planet faster than it's able to compensate. So let's think very quickly about the carbon cycle. So this is probably the carbon cycle you might have been taught a little bit about at school. So we have the atmosphere. Through photosynthesis, plants are taking CO2 out of the atmosphere and converting it into sugars in their tissues. These plants are then eaten by animals. So the carbon goes into the animals and becomes part of their shells and bodies and things like that. And then the animals, they respire, they breathe out, and then of course they die. And that respiration puts the carbon back into the atmosphere. So we have this cycle of carbon getting taken up by plants, eaten by animals, and then respired back into the atmosphere. This is the carbon cycle, but this is the short-term carbon cycle. This is the carbon cycle that's done on ecological timescales. This is being done sort of on the period of hours to at the shortest point is very, very fast indeed. But there's also another carbon cycle taking place, and that's the long-term carbon cycle. And that is things like volcanism. So volcanoes are putting CO2 into the atmosphere. These plants and animals, they become fossilized and they get calcium carbonate deposition. This takes some of the carbon out of these plants and animals and puts it into the earth, where it eventually becomes things like oil and limestone and coal. This takes millions of years. This carbon that's then present in the Earth's crust often gets pushed into the Earth's core through subduction. Through convection, it gets moved around inside the Earth's core and eventually gets fired out in volcanoes. This carbon cycle takes millions of years in the green. In the blue, it's happening almost instantly. So you have these two carbon cycles, one that's going very quickly and one that's taking millions of years. And the problem with human activity is it's short-circuiting this long-term carbon cycle. What we're doing is we're taking carbon from this pool that's built up over millions of years, and we're firing it into the atmosphere on a time scale of hours, days and weeks. So we're taking this cycle, bearing in mind this has taken millions of years to build up, and we're shooting it back out into the atmosphere much faster than it's able to go back in again. It's this disruption of the carbon cycles that is what is causing the issues with increased CO2 in the atmosphere. So for the past 12,000 years, CO2 levels in the atmosphere have actually been relatively stable between 260 and 280 parts per million. Before the Industrial Revolution, carbon in the atmosphere was about 280 parts per million. Currently, today, it's over 400 parts per million. We as humans have experienced carbon this high before, but at the time we were called Australopithecus afarensis, and we looked a bit like this. So it's been a long time since we've encountered this sort of level of carbon. Now when it comes to CO2 emissions, the USA is the world leader in CO2 emissions. So if you look at the metric tons of carbon per person per year, we are about over twice as high as the European Union, which is the next place in terms of height. But none of you include industrial extraction. Australia then leads all of a sudden, because Australia is bizarrely still a major coal producing nation. Australia's biggest industry is still coal, and so as a result, it's actually beating the US in terms of industrial extraction. Canada then comes screaming up behind the USA because of the tar sands in Alberta. So let's have a look. We talked about the carbon. Now let's have a look at the temperature anomaly. So this is how this zero line is the average, and we can see that over the past sort of 100 years or so, prior to about 1930, all the years were lower, and then suddenly we get the situation where most of the years are higher. If we look at it on the spatially, we can see it's not universally distributed. So we can see the red is hot, the blue is cold. We're seeing generally almost universal heating around the entire world, but there are these big hot spots in the poles. Okay. Now these changes in temperature and particles are leading to massive sea ice retreats. So these are two satellite images of the polar ice caps. You can see they're taken on the North Pole. You can see they're taken on the same day, which is, let me work out what month that is. August 7th, so September the 20th, 1918, September 20th, 2012. Same day, look at the difference in the size of the ice cap in 1980 compared to in 2012. So we've got massive sea ice retreats. In addition, we're seeing the extinction of glaciers. This is Mount Kilimanjaro in South Africa. This is what it looked like when I was born, so it's a massive mountain covered in glaciers. This is what it looked like recently, and an image taken from an aeroplane. That's what's left of the glacier. This is actually an image about 5 years old. Those glaciers don't exist at all anymore. Mount Kilimanjaro no longer has glaciers in the slightest. So we get to this question where, despite the evidence we've seen, we can ask, well, why doesn't the American public believe climate change? Well, there's a couple of reasons. In fact, there's a myriad of reasons. One, people don't look at evidence. A large part of this class that I'm trying to get into is teaching you how to read graphs, how to interpret data. Most people don't do that. They don't look at graphs. They don't look at the data. If somebody tells them something, they'll say, oh yeah, fine, if it's especially what they want to hear. Even if they do look at evidence, they can decide just not to believe it. We can shout things like fake news and just dismiss it. We can say things like alternative facts. We can just decide not to believe evidence, even if we do look at it. Even if we get past this stage, evidence influences decisions. It does not make decisions. Decisions are made by people, and people make those decisions on the basis of evidence, but they can just decide to ignore it. If other evidence tells people what they want to hear, then they can decide to believe that instead. It's much nicer when you're being confronted with bits of evidence to instead latch on to the bits that just reinforce your current worldview rather than the bits of evidence that challenge it. In addition, evidence can be distorted with lots of nice flashy graphics and things like this. I'm just going to show you one example of that. This is this YouTube video here, so I'm just going to stop sharing this screen, start sharing another. Where is my... Here we go. Let's start sharing that. Let's full size this. And I'm going to ask you a question about distorting of evidence and what this actually means at the end of this video.
For the past 250 years, Earth's atmospheric carbon dioxide, or CO2 concentration, has increased by 37%, from a pre-industrial value of approximately 280 parts per million to a value of about 385 parts per million today. And if current trends in fossil fuel use continue, many scientists predict it will climb even higher, reaching a value somewhere between 700 and 1,000 parts per million by the end of the century. Much discussion revolves around what may or may not happen to Earth's climate as a result of this increase. But what are the prospects for Earth's plants? We all learned back in grade school that CO2 is good for vegetation, and that plants need it to grow and construct their tissues. Might not the extra CO2, projected to be in the air by the end of next century, therefore actually be beneficial for the planet's vegetation? According to a recent study of one of the world's major food crops, the answer is a definite yes. In this study, sugarcane plants were grown out of doors in open-top chambers under natural conditions for nearly an entire year. Some at the ambient or current CO2 concentration of the air, and some at nearly twice that value. So what did the researchers find? At the end of the experiment, the plants grown in the CO2-enriched air showed increases of approximately 17% in height and 29% in leaf sucrose or sugar content. What is more, at the time of final harvest, the CO2-induced increases in leaf and stem biomass were 25% and 60% respectively, leading to an overall increase in total plant biomass of 40%. Based on these observations, it is clear that the ongoing rise in the air's CO2 content is destined to bring out the best in sugarcane, just as it does for almost all of Earth's plants, as we have extensively documented in the plant growth data section of our website. So just as you learned back in grade school, carbon dioxide is neither a pollutant nor a major source of global warming. It is a vital resource that is essential to the well-being of nature and humanity alike. Carbon dioxide, the elixir of life. How sweet it is.
Okay, so that piece of evidence, that video showed a whole bunch of nice fancy graphics and nice dramatic music to show you how important it was. But it talked about this experiment where they added extra CO2 to a bunch of plants and those plants grew more. That experiment is entirely true. That was done. It was published in the scientific literature. It is entirely correct. What he neglected to mention is what else they did in that experiment. So we've talked a bit about competition among plants and limiting resources. The issue with CO2 is there is nowhere on the planet where carbon dioxide is a limiting resource for plants. What limits plant growth is not access to CO2 for the entire planet, it's access to nutrients, or in some cases sunlight. So in order for that experiment to work, in order to get that increased growth that they observed, they had to fertilize those plants to an extent that is not observed anywhere in nature. Because otherwise, it didn't matter how much you changed the CO2, the plants didn't grow any bigger. Because what's limiting plant growth is not CO2, it was nutrients. So although that's totally correct, although what they talked about, that evidence was presented in the paper, they neglected to mention that CO2 is not limiting for plants, they're limited by nutrients. So this is a great example of a little distorted piece of evidence, not telling you the whole truth, and when it's told to people who want to believe that climate change is a good thing or doesn't exist, it totally reinforces that worldview. Okay, that video is taken from this website, which is called www.co2science.org. It is well worth a bit of your time. It is fabulous. It is. To be honest, it's just straight propaganda, and it's funded by Enron and a whole bunch more of the big fossil fuel industries, but it's worth a bit of your time. Okay. So, why don't people believe climate change generally? Well, one of the reasons a lot of people don't believe it is it's always presented as a debate. So whenever they're talking about climate change, whenever they're discussing it on the news or something like that, they will have someone who is for climate change and someone who is against climate change, and those two will go backwards and forwards. So people think in their minds, it reinforces this view, this is all a debate. I'm going to put these slides up online. I'm going to show you these two videos. I'm not going to show you this one because it is owned by HBO and I don't want them to take down this YouTube video because I've included it in it. But please watch it. It's well worth a bit of your time. But we can watch the others. So for example, let's do one of these little climate change debates. First of all, we're going to watch a video that suggests that, okay, climate change is entirely a hoax. Let me just share the screen. Here we go. And the one thing I want you to look at in this, while we're going through, there's one thing in here that is just entirely incorrect, but let's see if we can find it. So, off we go.
What are two of the dirtiest words in the English language? Well, if you're concerned with global warming, as so many people are these days, the answer is obvious. The two words are carbon dioxide, or as it is known by its chemical symbol, CO2. One atom of carbon and two atoms of oxygen. If we pump much more of it into the atmosphere, the argument goes, we're going to alter the climate, catastrophically. According to the Intergovernmental Panel on Climate Change, the IPCC, CO2 emissions from fossil fuels, which constitute 85% of our energy use, must be reduced to zero by 2100. If we don't save ourselves from ourselves, we're toast. That's the claim. Here's what's strange though. All life is carbon-based, and the carbon for all that life originates from carbon dioxide in the atmosphere. All of the carbon in the fossil fuels we are burning for energy today was once in the atmosphere as carbon dioxide before it was consumed by plankton in the sea and plants on the land. Coal, oil, and natural gas are the remains of those plankton and plants that have been transformed by heat and pressure deep in the Earth's crust. In other words, fossil fuels are 100% organic and were produced with solar energy. Sounds positively green. If there were no carbon dioxide in the Earth's atmosphere, the Earth would be a dead planet, period. Talk about catastrophic climate change. Take away CO2 and you'd have it. And yet the U.S. Environmental Protection Agency has deemed this essential ingredient for life a pollutant. But how can something that makes life possible be bad? Before I deal with that question, let's get clear on our terms. It has become common to refer to the emissions from burning fossil fuels for energy as carbon emissions. That is entirely misleading. Carbon dioxide is not carbon. Carbon dioxide is a colorless, odorless, tasteless gas which is an indispensable food for all living things. Can you have too much of it? In theory, yes. That's what climate alarmists say is happening now. CO2 levels are getting too high. Are they right? Well, if we look at the big picture, we find something surprising. For most of the history of life on Earth, carbon dioxide has been present in the atmosphere at much higher levels than it is today. During the Cambrian explosion, when multicellular life first came on the scene, CO2 levels were as much as 10 times higher than they are today. From a big picture perspective, we're actually living in a low carbon dioxide era. The optimum level of CO2 for plant growth, for example, is 4 to 5 times what is currently found in our atmosphere. That's why greenhouse growers worldwide actually inject additional CO2 into their greenhouses. They want to promote plant growth. Likewise, higher CO2 levels in the global atmosphere will boost food and forest productivity. That will come in handy, since by mid-century we will have to feed 8 to 10 billion people. In fact, we're already seeing the positive effects of increased carbon dioxide now. Satellite measurements have noted the greening of the Earth as crops and forests grow due to our higher levels of CO2. It turns out that carbon dioxide are not dirty words after all. We should celebrate CO2 as the giver of life that it is. I'm Patrick Moore, co-founder of Greenpeace for Prager University.
So, again, there was great bits of manipulation and some good half-truths in there, but my personal favourite is, I have to find, this gets me every single time. I'm going to re-show this one bit. When he talks about this bit.
The atmosphere as carbon dioxide before it was consumed by plankton in the sea.
No! Plankton in the sea, this is an animal, does not eat carbon dioxide. That is just spectacularly wrong. So, before we go into anything else, That's a no. But there's an awful lot of other half-truths in this. There's things about, yes, the greening of the earth that he talked about. This has been put down predominantly to the fact that we now dump an awful lot of nutrients onto the earth at the same time. The reason it's becoming green is because we fertilise our crops an awful lot more. So, again, nice flashy graphics. It gives all the right messages. It's rather convincing. So, let's go to just another one. This is going to be the last video I'm going to show you. Let's have a look at the other side. It's not a hoax. This video is about the same length. Let me start sharing. Okay, here we go. Let's make this big.
In 1960, Carl Sagan's PhD thesis included the first calculation of the runaway greenhouse effect on Venus. This was part of a career-long interest in the atmospheres of the planets, including our own. In the original Cosmos series in 1980, Carl Sagan warned,
"We are releasing vast quantities of carbon dioxide, increasing the greenhouse effect. It may not take much to destabilize the Earth's climate, to convert this heaven, our only home in the cosmos, into a kind of hell."
incoming light from the sun hits the surface. The Earth absorbs much of that energy, which heats the planet up and makes the surface glow in infrared light. But the carbon dioxide in the atmosphere absorbs most of that outgoing heat radiation, sending much of it right back to the surface. This makes the planet even warmer. That's all there is to the greenhouse effect. It's basic physics, just bookkeeping of the energy flow. There's nothing controversial about it. If we didn't have any carbon dioxide in our atmosphere, the Earth would just be a great big snowball, and we wouldn't be here. So a little greenhouse effect is a good thing, but a big one can destabilize the climate and wreck our way of life. All right, but how do we know that we're the problem? Maybe the Earth itself is causing the rise in CO2. Maybe it has nothing to do with the coal and oil we burn. Maybe it's those damn volcanoes. Every few years, Mount Etna in Sicily blows its stack. Each big eruption sends millions of tons of CO2 into the atmosphere. Now, combine that with the output of all the other volcanic activity on the planet. Let's take the largest scientific estimate, about 500 million tons of volcanic CO2 entering the atmosphere every year. Sounds like a lot, right? But that's not even 2% of the 30 billion tons of CO2 that our civilization is cranking out every year. And funny thing, the measured increase in CO2 in the atmosphere tallies with the known amount we're dumping there by burning coal, oil, and gas. Volcanic CO2 has a distinct signature. It's slightly heavier than the kind produced by burning fossil fuels. We can tell the difference between the two when we examine them at the atomic level. It's clear that the increased CO2 in the air is not from volcanoes. What's more, the observed warming is as much as predicted from the measured increase in carbon dioxide. It's a pretty tight case. Our fingerprints are all over this one. How much is 30 billion tons of CO2 per year? If you compressed it into solid form, it would occupy about the same volume as the White Cliffs of Dover. And we're adding that much CO2 to the air every year, relentlessly, year after year. Unlucky for us, the main waste product of our civilization is not just any substance. It happens to be the chief climate-regulating gas of our global thermostat, year in, year out. Too bad CO2 is an invisible gas. Maybe if we could see it. If our eyes were sensitive to CO2, and perhaps there are such beings in the cosmos, if we could see all that carbon dioxide, then we would overcome the denial and grasp the magnitude of our impact on the atmosphere.
So, give me a second, let's close this down. So that's one of the issues why we often get a lot of people don't believe climate change, because it's presented as a debate. There we had 2 videos, equal length, one for climate change, one against it, and if you saw those 2 videos and nothing else, you would assume, okay, this is still a debate, there's still 2 sides of this. But that's not quite how science works. I'm going to start sharing the screen again. This last video is, I'm going to not show, but I would like you to look at it after you've watched this. So why don't people believe climate change? Well, there's always a new natural explanation. There's always things like solar flares, volcanoes, the Earth has moved closer to the sun. These sort of explanations get handed out all the time. And the issue with coming up with a new natural explanation is somebody can come up with this idea and it takes seconds. To disprove it can take years. So we have a situation where people can come up with these things saying, oh, well, there's this natural explanation, and there's a years or so delay before it's disproved. So that's the problem. In addition, and this is a critical one, accepting climate change, accepting it is accepting that we are the baddies. It's accepting that we're doing something that's destroying our planet. Nobody ever likes to think that they're the baddies. And so if you've got a piece of evidence, even if it's completely wrong, telling you that what you're doing is just fine, then you're more likely to believe that than to accept you are the baddie. And I just like this meme for some reason. It came in, this idea of you either die the hero or you live long enough to see yourself become the villain. We are sort of refusing to see ourselves as the villains. Okay, just one last piece of evidence for climate change. That's a nice silly way to end quite a difficult lecture, is this image of underwear size. So going back to the 18th century, about the start of the Industrial Revolution, if we look what's happened to underwear over that time, that's been put forward as proof of global warming. Okay, so by the end of this class, you guys should be able to explain what global warming is and the difference between climate and weather, compare the different sources of evidence that we have and how they relate to climate change, and understand why climate change is not universally accepted. I'd just like to remind you, watch that 3rd video on YouTube. I can't put it on because it's copyright protected. Okay? Well, that is as far as I wanted to get to today, and I will see you next time.